So in this video, we're going to talk a little bit about what to look at to judge whether or not the speed of an object moving along a straight line is increasing or decreasing. So a little bit of background information here that you need to understand in order to make sense out of what we're about to discuss. This applies to a situation where you've got a function that represents the position of an object moving along a straight line. That line can be the x-axis, can be a horizontal line, could be the height of an object, just vertical motion being considered only, not horizontal motion. So not two-dimensional motion, but linear motion. When you have linear motion in your Calculus 1 course, you've obviously talked about the derivative of position representing velocity. Velocity is the rate of change of position. So the first derivative of position gives us a velocity function. But then acceleration is the rate of change of velocity. So the second derivative of position, or the first derivative of velocity, gives us an acceleration function. And then the easy way for us to think about speed in calculus is just to think of it as the magnitude of velocity. And that's probably also something that you've said if you've done a little bit of work in physics. In calculus, this equation right here is not true. Speed does not equal velocity all the time. We take the absolute value of velocity in order to generate speed. So absolute value of a positive remains positive. So speed does equal velocity if velocity is positive, but if velocity is negative, speed takes that sign away using the absolute value to generate our result. On this screen here, you see a graph of a velocity function. And what we want to try to do with this velocity function is we want to see if we can use it to try to see where speed is increasing and where speed is decreasing. Now, if speed is the absolute value of velocity, speed will be increasing if the velocity is moving further from zero, but speed will be decreasing if velocity is moving towards zero. So if you look at this stretch of the graph right here, that stretch of the graph has velocity, right? My y value on this graph represents velocity. This stretch of the graph has velocity moving toward the t-axis, toward the horizontal axis. The horizontal axis is where velocity is zero. So on this stretch of the graph, velocity is moving toward zero. Therefore, speed is decreasing on that stretch of the graph. Now, are there any other portions of this velocity graph where the graph is moving toward the horizontal axis? And if you think about the stretch of the graph from here to here, there's another stretch of the graph where the velocity is moving towards zero. We're moving away from zero here, but then on this interval here, we're moving back toward zero. So I think on those three intervals, speed is decreasing. How do we know? Velocity is moving towards zero on each of them. Now, where do we have the graph moving away from zero? So the graph is moving away from zero on this stretch of the graph here, right? We're positive and we're getting more positive. It's moving away from zero on this stretch of the graph down here. We're negative and getting more negative, and it's also moving away from zero on this stretch of the graph right here. We're positive and getting more positive. So speed is increasing on those intervals that we just highlighted in pink. So when your velocity is moving towards zero, speed decreasing. When velocity is moving away from zero, speed increasing. Now, another way that you can pursue this, now you basically need to have access to graphing technology in order to go about the work the way that we're going to discuss on this screen here. Top of the screen, you see the same velocity graph that we just were looking at. I also graphed a speed function. So I took the absolute value of velocity and I graphed that. So you see all those stretches where the original graph was negative are now flipped up above the horizontal axis. Now, what did we say about this first stretch of the velocity graph? We said that speed is decreasing because the velocity graph is moving toward a value of zero. Check out the speed graph. Now, this graph is obviously decreasing on that same stretch of t values. So if you have access to a graphing calculator or Desmos, like I built these graphs within, you can graph the speed function. It might be a little easier. Speed is decreasing, speed is increasing, speed is decreasing, increasing, decreasing, increasing. But what if you don't have access to graphing technology? What if you're going to have to rely on just some by-hand calculations in order to make these judgments? What do you do then? So I have a couple little portions of those velocity graph, of that same velocity graph, cut and paste it onto this screen. There are basically 4 different situations that you have to be aware of. Now, although there are 4 overall situations, there's a nice little result that we'll get to by the conclusion of this that should make this a pretty easy thing for you to try to tackle. If you look at this particular graph here, if this is a stretch of a velocity graph, here's the horizontal axis. So here we see the velocity is moving away from 0, right? My velocity is positive and it's getting more positive. I know velocity is positive on that interval. This is a graph of velocity. How do I know acceleration is positive on that interval? Well, acceleration is the derivative of velocity, and on this stretch of the graph, my slope of the graph is positive, right? On a velocity graph, the slope of the graph isn't going to indicate the value of your acceleration. So because slope is positive and the y value is positive for this stretch of the velocity graph, both velocity and acceleration are positive, that's a situation where speed is increasing, right? This stretch of the graph is moving away from a velocity of 0. If you drop down to the bottom left corner here, here's another stretch of a velocity graph. Here's where velocity is 0 on the horizontal axis. On this stretch of the velocity graph, velocity is moving away from 0. Speed is therefore also increasing. And what do we know about velocity and acceleration on this little piece of the graph? Well, velocity is negative, right? My y value is below the horizontal axis. My slope is also negative, so my acceleration is also negative. So the nice thing about what we've said on the left side of the screen here, if velocity and acceleration are working with one another, if they're both the same sign, speed is going to be increasing. Now check out what's going on over here. Here's a place where the y value for velocity is positive, but the slope is negative. Positive velocity, negative acceleration. This stretch of the graph is moving toward the value of 0. Speed is therefore decreasing. This stretch of the velocity graph is also moving toward a velocity value of 0. So speed is also decreasing. On this graph, velocity is negative, but slope, acceleration, is positive. If velocity and acceleration are working against each other, so if they have differing signs, our conclusion is going to be that speed is decreasing. So same sign for velocity and acceleration, speed is increasing. They're working with one another. If they're working against each other, speed is going to be decreasing, differing signs for those two calculations. So we'll wrap this video up with an example similar to what you might see in a calculus textbook, maybe even in a free response question if you're taking AP calculus. So this problem says the function f of t, shown below, represents the position of an object moving along the x-axis at time t. Determine the velocity at time 2. Determine the acceleration at time 2. Where is the object moving, left or right, at time 2? And is the speed of the object increasing or decreasing at time 2? So to answer those first 2 questions, I'm going to need to use some derivatives. Generate my velocity function by taking the derivative of position. So I take that derivative with a power rule, so nothing too crazy about that. And I end up with 4 when I put 2 in place of all of those values of t in my velocity function. Similarly, I'm going to push this derivative one step ahead when I'm doing my acceleration calculation. So I find my acceleration by doing the derivative of velocity. So I've applied a power rule to this to generate my acceleration function. I evaluate that at 2, and I end up with -1. In which direction is the object moving at time 2? Well, this velocity is positive at time 2. That tells me that the position is increasing, and if the position on the x-axis is increasing, that tells me my object is moving to the right at that time. Now, the thing we've been really geared at talking about for the majority of this video is this final question: is the speed of the object increasing or decreasing at time 2? The mistake I see students make too much is to look at this, see, hey, velocity is positive, speed's increasing. You need to figure out how the interaction between velocity and acceleration is working at the appropriate time, in this case 2, in order to make that judgment about speed. We know the velocity at time 2 is positive. We know the acceleration at time 2 is negative. Because velocity is positive, but acceleration is negative at time 2, we know the speed of the object is decreasing at that time.